In this video, we will talk about the concept of attention. It can be used to improve natural language translation, but it is also the foundation for the transformer architecture, which has been very impactful in the last few years, especially in the natural language processing. But let's talk about why we do need attention. To motivate the need for attention, consider the case where we want to translate a long sentence, a very long sentence. The encoder needs to capture the entire meaning of this sentence in its intermediate representation. So here we have the encoder, and this is the intermediate representation of this example of very long sentence. We want to translate it into another language, and then the encoder will need to decode this sentence from that intermediate representation. But we as a human would translate this sentence more likely that we would scan back and forth, start writing something, move back, try to figure out that the entire sentence is covered. We can think of attention as mimicking this process. Let's look at slightly different architecture of our encoder-decoder network. So instead of providing the intermediate representation or the context as a starting internal state to the encoder, we can provide it as the input to the decoder for all the time steps, together with the autoregressive inputs. So this is the network unrolled in time. This is the sentence in French, and we wanted to translate it into English. This is the encoder, and this is the decoder. The resulting network architecture looks like this figure. It's very similar to what we have seen before, but we have the context provided as input to every time step for the decoder. We want to enable the decoder to dynamically focus on different parts of the context at different time steps. So in this slide, we see a simplified view of the solution we just looked at. The encoder produces a vector of a fixed length that is the output at the last time step. The vector is then decoded by the decoder. However, to provide more information, we can instead capture the vector from the encoder at each time step. Given that we have 3 input words, as you can see here, we have 3 input words, we will end up with 3 input vectors. We can now use attention to let the decoder dynamically decide which of these 3 vectors it should focus on for each of its decoder time steps. The process of attention starts with computing an alignment as alignment vector for each decoder time step. This alignment vector consists of one weight for each encoder time step. For the first alignment vector, we see that the most of focus will be on the first encoder time step because its first entry has the weight 0.8, which is the largest value. We will use this alignment vector to compute the weighted sum of the intermediate state provided by the encoder. This will produce the input that is used to the first encoder time step. So in this figure, here you can see being red because most of the weight was on the red time step from the encoder. Then we do this for the other time steps as well. One interesting observation is that the third decoder time step this one, we see here both the second and the third input time steps, the blue and the yellow, have similar weights. That is, the input to the third time step for the decoder will be a mix between those two, which is shown in green, this one. So we have here mixed the blue and the yellow inputs because they have similar weights. On this slide, you can see we add the attention to our encoder-decoder network, and it implies changing how the encoder and decoder are connected. We will connect them with a attention structure. The input to this structure is the intermediate state for all the encoder time steps. As you can see, this is the input for this attention structure. We will then compute the weighted sum where the weights are adjustable and will change from time step to time step. Let's look at the unroll in time. So this is the illustration of second decoder time step with word am. So here, the output from the decoder time step 1 will select the weights that then are used to compute the input to the decoder time step 2. This one. Now, a key question is how do we compute these weights, also known as alignment vectors? We will compute the weights using a neural network. So as you can see here, this is the neural network to calculate the weights. This means that we can also train it to do the right thing with back propagation, and we don't need to worry about how to select these weights. So in this figure, we have two-layer neural network that is replicated n times, where n is the number of encoder time steps. We will apply the softmax operation. So the sum of all these outputs are 1.0. And this then used as alignment vector, the output of the softmax. To describe this more precisely, let's use matrix notation. We start with computing a score for each encoder time step. We do this using a two-layer network where tanh is activation function of the first layer, and we then multiply by vector v, which is a single output neuron without an activation function. We then apply softmax to scale the score values to end up being 1.0. And we arrange them into a vector known as alignment vector. However, this is not the only way to create an attention mechanism. We can reduce the number of layers so we can have a simpler network. We can even simplify it further to just make a dot product with no trainable weights. And this is actually the most common way to use attention nowadays, to use dot product. This figure shows how to use attention for neural machine translation, where we translate from French to English. We see on the left the French sentence and the corresponding English sentence. On the right, we show how the attention mechanism are focusing on different parts of the French sentence as it is translating to English. So on the y-axis, we see the French words, and on the x-axis, we see the English words. And we see highlighted diagonal suggesting that we more or less focus word by word. However, when we get to the expression European Economic Area, something interesting happens here. The word order for this expression is different in French than in English. And we see that the attention mechanism lets the model focus on all three words at the same time. So it's translating this as an expression rather than word by word. This highlights the benefit of using attention when doing natural language translation. So as this is the next step, we will see how this will be used in the transformer architecture in future videos. One thing I want to mention, some terminology, the query key value, and this is very important to understand. You can listen to it if you didn't understand at the first time. The query is the state or the data that is sent from the decoder. It is sent to the attention mechanism. The key is the data is used together with query to compute score. Dot product attention. In other words, we take the query and then we do the dot product between that and the state from the encoder. So the state from the encoder acts as the key. The value is the data that normalized score is multiplied by. In other words, when we did the dot product, we computed a score that we then normalize, and this score is then multiplied by the data from the encoder. So this data from the encoder is known as the value. An alternative view of this is that we take the query and it's matched against a key. The dot product will be of high magnitude if the query and the key are similar. And then we use that to retrieve the value corresponding to that key. In other words, query is matched against multiple keys to retrieve a value.